Okay, good afternoon. Can you hear me? Does this work? Okay, good. So today we continue with the missing pieces from transmission lines and then switch to a new topic. So let me start by summarizing what we heard last week. So any pair of parallel conductors that are reasonably close together forms a so-called transmission line with ideal transmission properties. That is, if you send in a signal on one side, it'll come out with exactly that shape, but a certain delay. If you build it as a transmission line, and so signals will then propagate undistorted with a finite velocity. So there will be some time between signal going in and signal going out, and the velocity is given by the speed of light in vacuum divided by the square root of the electrical, what's it called? Dielectric constant, sorry. So one of the most important characteristic numbers that is associated with a transmission line is the characteristic impedance, which is an ohmic resistance. And so the interesting feature is that an infinite transmission line behaves exactly like an ohmic resistor. So if you look into the input of an infinite transmission line, you cannot distinguish it from a resistor with value Z0. And if you design lines for fast signals, you must treat them as transmission lines, and you must also design them as a transmission line. So there must be some parallel conductor that carries the return current, and you have to have constant distance to have constant impedance. So whenever the rise time or the pulse duration of your signals is much smaller than the propagation delay that you expect for your line, then you really must treat it as a transmission line. If it's if the line is short and your signals are slow, you can just treat them as an ideal wire or a capacitance maybe. If you have long lines, you must take care of reflections. So whenever there's a change in impedance or an end of a line and you don't terminate it properly, you will have reflections of your signal, and they can lead to distortion and in digital cases, for instance, transmission errors. So that's a little bit like when you have a swimming pool and you just have walls on the side, the waves that are on the pool, they will always propagate back and forth, and you will have a very rough surface on your water. But if you want to have a smooth surface, a quiet water, then you have these pools where the waves that arrive at the edge just spill over the wall and disappear. And then you get a very nice, smooth water level, and that's what you want also when you transmit signals. You don't want all these distortions from signals that have already traveled through the transmission line a while ago. You want this to be clean. And that's why you always need to do terminations and impedance matching. And so when you use these LIMO cables here, for instance, we often have them in the laboratories. They have a small label with the transmission time. So this one is a 0.5 nanosecond cable. And the other thing you often use will be these little 50 ohm resistors that you can plug into a cable to terminate it. So usually when you work with transmission lines in the laboratory, you have a box of these things lying around somewhere. Okay. The thing we didn't get to last time was how to split a transmission line. Sometimes you want to send a signal from one transmitter to two receivers. And it's tempting to simply split the line into two lines at some point and terminate those properly. The problem is that this will not work, because these two cables in parallel will look like two 50 ohm resistors in parallel, so in total like a 25 ohm resistor. Okay, so this point as seen from this transmission line is terminated with 25 ohms, so you will get reflections. And these reflections will then travel back to the transmitter, where they're reflected again and come back here. So when you do something like this and you send a pulse from here, and you look at what you receive at this point, you will see, in fact, a series of pulses, because they travel back and forth from this point every time they are reduced a little bit because part of the energy is of course transmitted into the lines that you split, but a part goes back to the transmitter, it's reflected again, and then you will see it again and again and again. So that's not the right way to split a transmission line. If you only in your system only have one single transmitter at any time, you can actually fix this by adding a single resistor in series with the two, right? So this is not what is shown here, but if you put a resistor between this cable and the point where you split, then the sum of the 25 ohms resistor that you put in and the two parallel resistors that you have will look like a exact termination. So there will be no reflection here, but you will see a reduced amplitude on the other two. So this configuration, of course, only works in one direction. So if another side, if then suddenly this point also tries to send a signal, then from this side you will see the wrong impedance again. But there is a way to do that. You can use these triangle configurations, for instance. So if you have at this point you put 3 resistors, and you want to make sure that coming from each side, the other two look as 50 ohms. So you must make sure that if you come from here, for instance, you see this resistance, and then the parallel of these two plus the impedance. So you have R plus 1/2, because the two are parallel, R plus Z0, and this must be the original impedance again. And then if you solve this, you get that each one of these resistors has to be 1/3 of the original impedance. So if you do something like this, you can in fact also split transmission lines into two, and it'll look like a perfect splitter. But whichever way you look, you lose amplitude. So that's why sometimes these are called 6 dB splitters, okay? Because you lose 6 dBs of amplitude here. And that always happens when you have passive splitters, so it's unavoidable. I mean, even if it was perfect in the sense that it doesn't burn any power in any resistors, you would still lose amplitude because you have to divide the power into 2 lines. So if you cannot afford losing amplitude in a splitter, you have to use an active splitter. So the warning here is that in these boxes with the termination resistors, you will also find these pieces here, which look like handy little splitters, but they're not meant for that purpose. So they're not meant to be used in this kind of situation because they have no resistors inside. So these are only used for splitting at the source. So you can put them directly on the output of a signal source and then drive the signal to 2 places. You cannot use them to drive the signal 5 meters through a cable and then split it into 2 smaller cables to the ends, to the users. The other use case for these is when you just want to spy on a signal. So you have a long line with many receivers, and they all want to look at the same signal. Then you can use these things to have the incoming cable on this end. You have the incoming cable here and the outgoing cable here, and you put the receiver here with no termination. Then you can just look at a signal that passes by. Okay, that's the other use case. They're not meant for splitting cables. Okay, a few words about lossy transmission lines. So far we talked about ideal transmission lines that where we have neglected the resistance of the cable, but when you have long cables, you have to also take that into account. And instead of these lumps of L's and C's that we considered so far, one has to take into account a possible line resistance, but also a possible conductance between the 2 conductors, which is not necessarily a real resistor, which is because the insulation between those lines is typically very good, but it can be dielectric losses in the material that you put in between. So when you have very high frequencies, that can be important, but usually it's not very relevant. On the other hand, here you have the ohmic losses of the wire. These wires are often very thin. And another important effect when you go to very high frequencies is the skin effect, which means that at very high frequencies, when you go into the gigahertz range, only the outermost skin of the cable is really conducting. So at high frequencies, the fields are pushed out of the conductor, and only the outermost microns of your conductor really contribute to conducting, and then the resistance goes up. That's the skin effect. And if you have something like this, and you try to calculate the impedance of this, you come to the conclusion that it's actually not a real number anymore. So now you have a complex impedance, and that automatically means that you have signal distortion. Okay, so not every frequency will be transported with the same amplitude, but different frequencies arrive then with different phases and different amplitudes. That means your signal is distorted when it arrives at the receiver. Okay. Normally, we assume that we have weak damping, so we still talk of the local properties of the ideal transmission line, but we have to additionally take into account that we have damping and distortion. And here's an example where you see a fast signal being transmitted through 1 meter of wire, and then a longer wire of the same size. And the longer you go, the more your signal is distorted from the original nice shape. And typically what you get when you transmit digital data, for instance, is that the fast step at the beginning of a pulse is delayed. And one countermeasure in digital transmission is, for instance, to use the so-called pre-emphasis. So what you do is then you, instead of sending a step that you really want to send, you overemphasize the start of the step and then go back to the level that you want to send. And that can compensate this if you know exactly what your cable looks like. So this is done here, for instance. We have a 2 meter, a very, very tiny twisted pair cable. You send, you have no pre-emphasis, and send a random pattern, then and overlay all the signals. Then you get this so-called eye pattern, where the color shows how often a signal goes through which point here. And when this eye closes, then the signal is no longer properly detectable on the other side. Okay, then it's very likely that you get the wrong bit here as a 1 instead of a 0, or a 0 instead of 1. And if you do the proper pre-emphasis on this cable, then you get a very nice signal again. So it can compensate some of the lossy features of imperfect cables when they're long. Okay, the last thing I want to mention is the differential transmission line. So in practice, when you really transmit fast data or fast signals over lines, long lines, it's often advisable to use differential signals. So you have not only one signal polarity, but you copy the signal with the inverse polarity and send both through the same cable on different wires. So you have 2 wires in your cable, and one signal goes up and the other one goes down by the same amount. And that signal is sent through these pair of wires. And this is much more immune to pickup and other problems that are coupled onto the wire from the outside. Okay, so with this kind of signal transmission, you're very much immune to external problems. There are different types of cables here. There's these so-called twin-X cables or twin coax cables. You often see these differential transmission lines or strip lines or simple twisted pair cables. In this case, there's not even a shield necessary. So these are like single transmission lines, but they're symmetric. So we have often considered transmission lines where the ground or the return is basically a perfect wire, and we only had the inductance on one side. But you can also look at it as a symmetric system where you have inductances both on the line and the return, and then this is basically what this looks like. What's worth noting here is that when you have such a system of 2 wires, then there are 2 modes of signals. So one is the one that you're usually using to signal data. So one goes up and one goes down. That's the differential mode or the odd mode. And this must be properly terminated here by having a resistor between the 2 wires. But there's also a so-called even mode when both lines do the same. This happens when you have distortions, for instance, when you have pickup, or when there's a ground bounce between the receiver and the signal, then there, in addition to the differential mode that carries the information, you also have the odd mode. This odd mode, in principle, should also be terminated, and it can have a different impedance. So to do this properly is a little tricky. It can be done with a network like this, where you have a termination pair here, and then a center tap to another resistor to ground, which terminates the common mode. This is often not done, but sometimes it's necessary. Okay. Does anyone have a question on transmission lines? Because now we will change topic. Okay, not. We now switch to diodes. So this is just a picture I found recently. It's a list which just shows that there are many, many different types of diodes. I don't even know all of them. And so let's start. The diode is, in contrast to everything we've seen so far, a nonlinear circuit element. So a resistor or a capacitor, you always have a linear response of the current, for instance, when you change the voltage. And this is not the case here. In fact, it's maximally nonlinear in the sense that the current in these diodes can only flow in one direction. So here you see the circuit symbol of a diode, which is this triangle and with a line, and the line is supposed to indicate blocking of the current. So the two terminals of the diode have the name anode and cathode, and that comes from a historic precursor of the diodes, which is the vacuum tube. Maybe you've seen these. They have a glass body, a vacuum tube, so there's vacuum in here. Then you have a heated cathode, and when it's hot, then it emits electrons into the vacuum, and you can apply an electric field then between this heated cathode and the anode, and the electrons can then fly in this direction, and then they return through the power supply here. There is obviously, since the anode is cold, no process that currents can flow in the other direction, so this implements this ideal diode where current can only flow in one direction. These are not used very much anymore, except in some very special cases where people think that their hi-fi equipment sounds better with these. But the names still stayed, so they're still called anode and cathode in the more popular or the more commonly used junction diodes that we use today. There's another type of diode which was historically actually invented long before the junction diodes, which is the so-called crystal detector. So early radios, people had a piece of semiconductor, germanium, I think, and then they had to push a needle onto the crystal, and this the interface between the semiconductor and the metal of the needle forms a rectifying system, and this is today called a Schottky diode. We'll come to that later. So diodes have many applications. The most important one is certainly the rectifier, which makes use of this property that the current only flows in one direction. So this can be used, for instance, for amplitude demodulation. We'll look at that example. But you can also then, if you look in detail into the properties of the IV curves of a real diode, use them for voltage regulation, but they also have protection applications. Okay. So here we have a photo of a small diode, a small switching diode. They have numbers typically starting in 1N, so 1 is for diode typically, and this 4148 is the vanilla flavor diode that you basically can use for almost everything. And they usually have on their body a line, a ring, and the ring corresponds to the position of this line in the circuit symbol in the diagram. And the current will then only flow in this direction, but not in the opposite direction. We will not look in detail at the moment at the curve, but only at the IV curve, but only use the idealized characteristic and see what we can do with such a curve. And at the idealized version is that when you look at the current versus voltage diagram, up to a certain threshold voltage, no current flows at all. And then if you go above this threshold voltage, it's an ideal conductor. So it's basically a short circuit. So this threshold voltage or diode voltage for silicon PN diodes is typically of the order of 0.6 to 0.7 volts. For other kinds of semiconductors, for germanium, for instance, it's 0.3 volts. And for the semiconductors that are used in LEDs, it's somewhere between 1.3 and 4.5 volts, depending on which material is used, because for different colors you need different materials. So let's look at the simplest application, which is the so-called half-wave rectifier, where you start with an AC voltage source, shown here, 5 volts in this case, which you send through a diode and then into a load, like a resistor of 1 k ohm in this case. And then here shown versus time is the AC voltage of plus or minus 5 volts, so 5 volt peak amplitude is the red curve. And then if you look at the voltage that you see here, that's the green curve. So it'll follow the input, but it'll be roughly this voltage drop below, because there is, you always have this 0.7 volt or so drop across your diode when it's in forward direction. But with this distance of 0.7 volt, it follows the input voltage until you get here. Now the input voltage becomes negative, and the current would then have to flow through the diode towards the voltage source, and it cannot do that, so this point stays at 0. The resistor fixes it at 0 because no current can flow anymore. So this point will just remain here until the voltage source becomes positive again, and then the green curve follows again. So you get this wavy curve, which is not really a DC voltage, but it has at least only one polarity. Okay, so you start with a signal that has alternating polarity, and what you get is a voltage that has only a single polarity. In this sense, it's a DC voltage, but it's of course not very flat. So what you do then is you try to smooth this by putting a capacitor at the output in parallel to your load. And this will improve your DC voltage. So now, as long as your input voltage is higher than the output voltage, the anode, the diode is conducting and will send current both into the load and charge the capacitor. And then when your input voltage starts to fall below the level that you have here, the diode stops conducting, so it turns off, and now the load must live from whatever is stored on the capacitor. And this is what you see here. The red now is what was green on the previous slide, so without any capacitor. Now we put different capacitors of increasing value here. I'm afraid the labeling is wrong. Of course, the shortest time is this one. So you follow the input curve to a certain point, then the input goes negative again, and then the capacitor is discharged through this resistor, and the RC time of this discharge is given by obviously the R of this resistor and the capacitor and the C of this capacitor. So if you increase the capacitor, the RC time goes up, and then if you make it very large, then the time becomes so long that this really starts looking like a DC voltage. Okay, and this way you have made a DC voltage, a reasonable DC voltage from your AC input voltage. So these capacitors need to be relatively large because they have to store the energy that is consumed by your load for almost 3/4 of a period. So they can only be charged when the input is higher than the output voltage. The obvious improvement is to use both half waves, and the way to do this is with these so-called bridge rectifiers, where you offer 2 different paths for 2 different polarities. And the result will be that in the load you always have the same current direction. So let's go through that. When the input voltage is positive, in this sense. So we have the positive voltage here and the negative voltage here. Then this diode blocks and this diode blocks, but these two conduct, and the current then flows from the source through this diode, through the load, and then out through this diode again and back to the source. Okay, so now you have the positive component here and the negative component here. Now, if you turn the input around, you get a negative voltage from your AC. This is shown here. Now, this diode blocks because this is the most negative node, but the current can flow from here, which is now the positive node, through your diode, through the load, and through this diode, and then back to your voltage source. And again, you have the positive sign here and the negative sign here. So in both cases, you get the same sign on your load, which is basically you have now two rectifiers that work alternatingly. When you have a floating source, which is, for instance, a transformer, which is often the case, so these bridge rectifiers are often used together with transformers, and the outputs of a transformer is floating. There's no direct reference to real ground, so you can just define one of the points as ground, for instance, this one, and then here you have a constant voltage, a good reference a voltage reference to ground. This is often drawn with a load put outside of your bridge rectifier, and then it looks like this. So here's an example of how that can be used. You have in the lab power supplies that you may be using, you come in with the 230 volt AC from the outlet, and there's a transformer here that steps it down to maybe 1/10 or so. So you come in with 20 volts here, go through your bridge rectifier. You put some smoothing also here, and then at this point, you connect your load. Here I have not connected any point to ground, so this is a so-called floating supply. And so if you have a lab supply that looks, for instance, like this one, you often have these three terminals. So there's the positive and the negative, and there's a ground pin, which is typically not connected directly to anything. It's still often useful or advisable to connect it to something, to the ground of your measurement device or whatever you want to measure. But these two pins are completely floating. Okay, that is very useful because you can then, for instance, you can stack two of these supplies on top of each other and add two voltages. What am I doing? Or you can operate, for instance, devices that don't need to sit around ground. They can sit at an elevated potential because your experiment operates at an elevated potential. Or it's also useful when you have supplies that are far away from your measurement. So you have 2 or 3 supplies that are distributed in the lab, and you have your test, which is far away in the corner, and you want to avoid so-called ground loops. Then it's always advisable to use floating power supplies. The catch is that it's not defined what kind of potential you find at the output, and so in the there is often some kind of protection here that makes sure that this voltage does not go too far away from ground. But that's only a safety measure. In the simulation exercise, you will simulate a transformerless supply, which does not have this feature, so the output is not exactly floating, and that makes it actually dangerous. So this is nice for simulating, but these devices, you should not build them at home. They do exist, they are in use, but they should only be in places where nobody can ever touch them, because it's not guaranteed that you do not have a direct connection from the input to one of the terminals at some point. So please don't build that at home. Simulate it in the exercise, but don't build it. But these are relatively safe. Okay. Good. Let's look at the simulation of a full wave rectifier. So this is you have the 4 diodes here. You come in with 5 volts and 50 hertz on this side. So the same configuration that we had before with the single diode rectifier. And now what you see for the same kind of capacitors, you have less droop during the cycle. So the first one went much lower. So with the same capacitor, you get much less ripple on your output. Yes? Yes. That's the black one is the negative. Then how does this work? Sorry, this doesn't. Physically, it's connected. So this one is really connected like it's shown in the diagram. So it's one point of the bridge. I don't know why my pointer stopped working. Oh no, it works again. So the black connector here is connected like this to one point in the bridge rectifier, and the red point is the opposite point in the bridge rectifier. The green one is not connected at all to this. It basically goes directly to the safety ground on your, or the earth on your plug. When you have a Swiss connector, you have these 3 pins. One is the neutral, one is the phase, and one is earth or safety ground. And the green one is typically directly connected to this earth. No, except that sometimes there is a device that limits the voltage between the black and the green. That could, for instance, be one of these diodes that we'll come to next time, I think, the Zener diodes. They limit the voltage between 2 points. So sometimes to make things safe, you don't want to have 10,000 volt between the two, because whatever you connected on the other side gives you a voltage of 10,000 volts. You don't want that to feed into your device that would either destroy it or endanger you. So sometimes there is something connected here that limits the voltage. Sure. Other questions? Okay. So if you compare this now with the simple rectifier, then you find that you get much less ripple for the same sort of capacitance, which is nice. So ripple is the amount of how much the output is wavy and deviates from constant. So the disadvantage is that now the current has to go through 2 diodes. So you have 2 voltage drops. So we start with 5 volts. And with a single rectifier, we went to 4.3, and now we're at 3.4. No, it doesn't make sense. What was 3 point something? 3.8, right? Yeah. No. Roughly 3.1.7, 3.6, yes. Okay, good. Just to note, there is also something with a similar topology, which has nothing to do with diodes. I just mentioned it here because it's interesting and will be more and more important, which can be viewed as an inverse bridge rectifier. So if you replace the diodes by switches and then turn on the switches alternatingly, you can do the opposite thing. So with the rectifier, we came in with an AC voltage and created a DC voltage. And if instead of the diodes, you use switches, you can also do the opposite thing. So when you, for instance, come in with 240 volt DC on this side with positive polarity here, and you open these 2 switches and you close these 2 switches, then you have the plus 240 here and the minus and 0 here, for instance. And if you then switch the other 2 switches and close these, then you have now the positive side goes here and the negative goes here. So you switch from positive polarity to negative. And if you do this periodically, then you get this sine wave output, which almost already looks like an AC voltage, but not quite. And you can make it look more like a square wave if you use so-called pulse width modulation. So if you don't simply switch these, turn these switches on and off, but you switch them on for a certain amount of time, and you make this time shorter when you want the output to be lower, and longer when you want it to be higher, and then you smooth this with the capacitor, then you can get a pretty nice sine wave. So this is the way one can make AC power from a DC power, for instance, from a battery or from a solar cell. These things are called power inverters. Unfortunately, because the name inverter is, I know at least 3 devices in electronics that are called inverters, but that's what they are. That's what they're called. So these, I think, will become more and more important in the future. Okay, but now let's come back to diodes. And one very simple application that you can do with a rectifying diode, which in fact was one of the first applications it was used for, was to use it to do demodulation of amplitude modulated radio. So how does that work? You start with some amplitude modulated signals. So you have a high frequency, so-called carrier signal. This is the fast oscillating signal that you see here, and you modulate it with a slowly varying amplitude. Okay, so the amplitude is this. This is the signal that you want to transport, and you use a high frequency carrier signal to carry your signal through radio waves or whatever. Then you receive it, and you want to recover the modulating signal again. So the first step here is then to take this signal and feed it through a rectifier. So this is a simple diode and a resistor. And what you then get is, of course, you clip away the lower part, and all you're left with is this still fast oscillating, but only going in one direction of your signal. Then the second part is to smooth out the signal. So you want to get rid of the fast oscillation. And one way to do this is, again, to use a smoothing capacitor, which washes out the fast oscillation. So this is now something that looks almost like you wanted to have. And the reason that it doesn't look good is that this is not an excellent filter. So you can add a bit of a filter here. And then, so we added a second low-pass filter here. And what you get in the end is something that is a voltage that has a single polarity and nicely reflects the amplitude of this signal. Okay, this is the principle of demodulation of an amplitude modulated signal. So it's interesting to look at what happens here in the frequency domain also. If you do a Fourier transform of the input signal, you get the carrier frequency and the sidebands. If the signal was not modulated, you would only have the carrier frequency. So there would only be a peak at the center. And now, due to the modulation, you get these sidebands as well. Georg has shown this in his lecture already. Then if you rectify the whole thing, you also get these very slow components that are near DC. So you introduce these signals here, and this is what you really want to have. So now these frequencies are really just a nuisance. You want to get rid of them, and all you want are these frequencies, and that's why we added the smoothing and the low-pass filter. So this is just a logarithmic version of the same thing. Here we had the linear plot, linear in frequency. What is more commonly shown is the logarithmic or double logarithmic version. So here you have again the input carrier plus the sidebands, which you don't really see here anymore. And then you rectify this, and you get the series of spikes here that are the signal that you really care about. Now again, in this double logarithmic plot, the so-called Bode plot, you can look at the action of your filter. And so the frequency response of your filter when you only do the smoothing is like this. It's like a single RC filter. And when you add this additional filter here, we can make it constant for a longer time, and at the same time falls more steeply at the desired frequency. So the higher the order of your filter, the steeper you can make this fall. And with the additional filter, we have a 1/f² drop of your transmission function here, and you can get a better separation between your carrier signal and the actual payload that you're interested in. And then the effect of switching from one filter to the other, you can see here. So this is somewhat a distorted signal where you suppress the high frequency components too much, and if you use this filter, you get better acceptance for your high frequency part of your payload signal while suppressing the carrier even better. So you get a much nicer signal here. Okay. Another application of diodes is a so-called peak detector. A peak detector is a circuit that takes an input voltage that varies over time and can then memorize the maximum value that you've ever seen. So if you have any waveform at this point, some signal that varies somehow over time, and you send it through this a diode into a capacitor, then whenever this part is higher than what is stored on the capacitor, there's a current flowing and the capacitor will be pulled up. So this capacitor follows the input signal up to the point where the input signal falls below the voltage in the capacitor. So when the input signal goes below the voltage in the capacitor, then this switch basically opens, and you in this way you only keep the highest value that ever occurred. So as an example, if this is time, for instance, and this is the black one is your input signal, which varies a bit up and down, then the voltage on this capacitor follows while it rises and then stays constant with separated by one diode drop. So there's always this 0.7 volt diode drop, but it doesn't go down again. So it stays here at this level until the input voltage goes higher again, but only up to this peak, and then it remembers the value of this peak. So that's why it's called a peak detector. It detects the peak value of a voltage. And then at some point you read out the voltage, reset the thing, and start again. Another application are so-called clamps. So now we have the diode connected to ground, but in the blocking direction. And we look at what happens. So now we have the voltage here that changes polarity. It sends a current through this resistor to your load, but the point here can only be positive. Whenever this is positive, this is fine, then the point here will just follow. But whenever it goes negative, the diode conducts, and it will basically not allow this point to become more negative than one diode drop. Okay, so it prevents this point from going below zero. This can be a safety feature, but it can also be used. This is, for instance, in the voltage converters that we'll talk to in the next couple of minutes. I think it's important to understand the difference between this and the rectifier. For the rectifier, which looked kind of similar, you also had this part, this input and that output. And here the diode was in series. But it is not a rectifier because in this circuit, the current can change direction. You can have a current that flows from the output to the input. So the input can pull the output back down again, okay, which it doesn't do for the rectifier case. Here the load has to pull down the output. Okay, that's an important difference. Something interesting now happens when you use these clamps together with a capacitor. So let's look at this circuit. We have this alternating voltage here. We have a capacitor and a clamp diode on the other side. So the output voltage now follows the input voltage as long as this voltage is positive. Okay, when this point is positive, then the diode blocks, and the capacitor has no choice but following. So there's no current flowing through the capacitor, so the voltage across the capacitor stays constant. So if this point goes up, this point has to go up as well. And if this point goes down, this point goes down as well. Okay, so what you see in this is basically this. The output goes up and goes back down again until you hit one diode drop negative, basically, until you try to go negative. Okay, At this point, the clamp now kicks in. So the clamp will do whatever it can to prevent this point from going negative. And while it does that, there's a current flowing through the diode. So now here we have the negative voltage here, and the positive voltage is here. So there's a current flowing through the diode, and this current charges the capacitor. So now we start storing a voltage on the capacitor, which corresponds to the amplitude of this sine wave here, the peak voltage of the sine wave. And now as the sine wave continues, this is at some point maximally charged. And then we start going positive again. So at this point, the output goes positive again, and the diode stops conducting. So there's no more current through the capacitor. So again, we start lifting up the capacitor. And since there's no current flowing, the voltage on the capacitor will stay, across the capacitor will stay the same. So we're lifting both sides of the capacitor up, which means that the output at this point goes up twice the peak voltage. Okay, so the input here at this point goes from minus peak voltage to plus peak voltage, and the capacitor can only follow this. So it goes up to twice the peak voltage. So and then in the subsequent oscillations, it basically just follows it and will never go negative again. So what we've done here is we came with an AC voltage of a certain amplitude, and we turned it into a DC voltage, which is still oscillating but shifted by one amplitude of the input voltage. Okay. And this is the fundamental building block of these voltage converters. So from now on, the output voltage follows the input voltage shifted by the peak amplitude. And we'll continue and see how we use that to use voltage multipliers after the break. Okay. Okay, so maybe it's helpful to look at this in another way. So the circuit that we have here with the alternating power supply, the alternating voltage on one side, and a capacitor and the diode going back to ground. Oops, hold on. Okay. If you look at it in another way, it's like this: when the supply voltage is negative, you can draw it like this. So here's 0. You have minus the peak voltage here, minus the amplitude here, and now you're charging the capacitor because this point is positive and this point is negative. So current can flow through the diode, and this current charges the capacitor. And so you have 0 volts here and minus V here. So across the capacitor, you have a voltage of plus V. Okay, and then you turn around this thing. So that's when the AC voltage goes positive again. The diode stops conducting. So in this position, you have still the charge on the capacitor, which makes this point plus V more positive than this side. But now we have plus V here. So in the end, you have 2 plus 2V on the other side because the diode doesn't conduct. So that's the principle of operation. So you charge it while it's negative, and then you lift it up, okay, and without current flowing through the capacitor. This is sometimes also called the principle of the flying capacitor. So you charge it in one position, and then you disconnect it, which is here done by the diode, and then reconnect it in another way, and then you have the same voltage difference, but at another potential. Does that make sense? So this is the fundamental principle behind all these voltage converters. Okay. So let's see this in action. You have this, we start with the same circuit that produces this kind of voltage that we've just seen. So it starts up here, and in the end, it creates this peak voltage that is twice the amplitude of the input voltage. So our peak voltage here is 5 volts, and we get to twice of that with this principle that we've just discussed. Now, you add to this a rectifier or a peak detector, which takes this red voltage and sort of peak detects it, right? So this circuit, the output here will then always get stuck at the peak voltage of this part of the circuit, okay? So this then approaches slowly twice the input voltage. And this is called, this circuit is called voltage doubler or Greinacher circuit. Greinacher is a Swiss, or was a Swiss physicist who invented this circuit. And this can be used to now really create DC voltages from an AC voltage that are higher than the amplitude of the AC voltage. Okay, it's called a voltage doubler, but in principle, it's strictly speaking only a voltage shifter. The circuit, as shown here, has only very limited ability to drive load. So I can, of course, such a circuit is only useful when I can drive a load. So here I attach the load, and what this load does is, of course, it discharges this capacitor when there's no new current flowing in here. So it'll go down a little bit. So this can only drive small loads. Now we'll just redraw the same circuit in a different way. So we go from this circuit that we had here and rearrange the components a little bit. So we take this part out, consider it as an input. Then we have the capacitor and the diode here, and we turn this diode and draw it here at the bottom. This capacitor, draw it at the bottom, and the second diode we draw here. So this point becomes this one, and this point becomes that one. Otherwise, it's the same circuit, I just draw it in a different way. And the reason why I draw it in a different way is that I can now view this as a building block that takes a voltage that goes from 0 to V0, oscillating, and creates an output voltage and a second voltage on top of the output voltage that oscillates up and down, but shifted by the output voltage, okay? And this is now something that I can use to feed into another voltage doubler. Okay, so we have from here to here twice the peak voltage, and here we have an oscillating node that goes up and down with twice the amplitude of the original AC voltage. And this can feed another voltage doubler, because what this at this point it doesn't need to be at zero. It can also be offset by something. And here we only need a voltage that goes between two voltages by an amplitude that is twice this peak voltage. So this whole thing can be used to feed another stage of the same type. Okay, this is done here, and so what you do when you do it twice, you have at the output you have 4 times the peak voltage here as a DC voltage, and another oscillating voltage that is shifted by another two amplitudes here, but still oscillates up and down and can drive yet another one. Okay, so here you see 3 of these staged together, and a simulation of how it starts up. So it's a little wavy at the start, but it finally reaches, then the output stage finally reaches 3 times twice the input amplitude. Okay, so we start out with a simple AC voltage, and then by cascading these Greinacher stages, these so-called voltage doublers, we get to a nice, much higher DC voltage. And this is called a Cockcroft-Walton generator, after the inventors who used it for particle physics accelerators in the 30s, actually. And these are in fact still in use. So you will find them in normal devices. Whenever you have a high voltage supply, there's very likely to contain a Cockcroft-Walton generator. Or when you buy these fly squatters, they probably also have that. But they're also used for particle accelerators still, which is what they were developed for in the 1930s, actually using vacuum tubes back then. They didn't have the diodes. And these are very well suited for generating extremely high DC voltages, because across each stage you only have you only have the same voltage. You don't have the full voltage across any component in this circuit. Okay, every block only sees one step of this voltage shifting, and the full voltage never appears except at the output, between the output and the input. So this is very suitable for making these things, and it is therefore usually the last stage for making making high voltages for particle accelerators, for instance. And here you see the Cockcroft-Walton generator of the Paul Scherrer Institute, which drives the proton accelerator, the first stage of the proton accelerator. It creates 800 kilovolts and 30 milliamps of current. And so the things that you see here crossing up and down, those are the diodes. Okay. A related principle are the so-called charge pumps. Instead of having an AC voltage, you use a DC voltage that you switch back and forth. And this is shown here. You have this chain of diodes, and they are connected, and these capacitors that are connected to these phase-shifted voltages that go up and down here. And then you have one phase where the charge is shifted. So you lift this one and you pull this one down. Then the charge flows through the diode from one capacitor to the next one, charging this one, and then you do it the other way around, and then always charging the capacitor from the previous stage. And this can also then increase the voltage that you put in. So you come in with the voltage V here, then this one goes up to 3 volts, and then here you go up to 5 volts. So these are so-called charge pumps. There's also another circuit that is also called charge pump in the PLL that I just discussed with Stefan. That's why I mentioned. But so these charge pumps can be used to generate higher DC voltages from a DC voltage. So the Greinacher circuit generates a high DC voltage from an AC voltage, but you can also do the same thing, more or less the same thing, to generate high DC voltages from lower DC voltages if you have alternating voltages that you can use for switching. And okay. Another voltage converter, which is used in the other direction. So the charge pump creates higher voltages. Sometimes you want to create lower voltages. So, for instance, when you have a long cable and you want to avoid losses on the long cable due to ohmic resistances on the cable, so it's more convenient to come in with a high voltage, but at the consumer, you need a lower voltage but a higher current. Then it's sometimes advisable to use these DC-DC converters to convert the high voltage with a small current into a low voltage with a larger current, like a transformer, but for DC voltages. So, and this is done the following way. You have a switch here, so you connect your DC voltage with a relatively high voltage. You connect via this switch to this circuit here. So the switch opens and closes periodically. So it chops the DC voltage into a quasi AC voltage, usually in the megahertz range, or relatively fast. And then you use this LC circuit to smooth the voltage. Okay. Obviously, you don't want to use an RC here, because that would burn a lot of power. So use the LC. So whenever the switch is closed, the current flows through the Yes. So when the switch is closed, the current flows from the voltage source through the inductor and the load and the capacitor, and then the voltage across the inductor rises. When you switch off the current, then the current flows through the diode, through the load and the diode here. Okay, and by selecting the duty cycle here of the switch, so how long is it on and how long is it off, you can select the output voltage. Okay, so this is simulated here, where you have a 10 megahertz switch, which has at this point 50% duty cycle. We chose 1 microhenry coil and a 10 nanofarad capacitor and a relatively small resistor as a load. And now what you see here is the current through the inductor and the current through the diode. And when you close the switch, the current through the inductor increases. This picture is better. It's difficult to read. Huh? So as long as you have a current, as long as you have the switch closed, the current here goes up. You store energy in the inductor, and then when you open the switch, the energy from the inductor is then taken back down again, and the voltage drop across the inductor basically makes sure that your load sees a lower voltage than the input voltage. Okay, and the effect is shown here. You see a voltage that is then lower than the input voltage. So you come in with 12 volts here, and you see this wavy output voltage that is now 6 volt because we have a duty cycle of 50%. Okay, so this is the so-called buck converter, and these are frequently used to come in with a higher DC voltage and produce lower DC voltages. And it can be regulated very easily through this duty cycle of this chopper. So these are used very frequently in PCs, for instance, where you use many different voltages. So you come in with 1 voltage out of your big power supply, but in your circuit you need 5 or 6 different other voltages, and then you use these DC-DC converters to generate all these voltages and to even regulate them and to change them dynamically. So your processor, for instance, will use different voltages at different times. Whenever when it runs faster, it needs higher voltage. So you can so these things are needed to regulate, to adjust these voltages. They're so frequently used that you can find the whole circuit now in integrated circuits that have the chopper and the diodes there, or often they have switches instead of the diodes also. They have the frequency generators all together in an integrated circuit, and you can use them. The only thing you have to provide is usually an inductor. Sometimes they even have an inductor inside, but often you have to provide an external inductor. And here's an example of a relatively bulky inductor, which is used in our experiment. So in order to get a reasonable inductance, you need sometimes relatively big objects. In this case, it's extremely big because it cannot have an iron core. So good inductors, if you want a high inductance, you usually wind your coil around a piece of iron. That was not possible in this case because this piece operates in a very high magnetic field, 4 Tesla magnetic field, and then the iron would be saturated and doesn't have any effect. So it had to be an air coil inductor. Okay. The last application of a simple diode that we have here now is a so-called flyback diode. These are needed when you switch inductive loads. So if you have a coil where a current flows through and you want to switch the current off at some point, you know that a sudden switching of the current will cause a high voltage across the diode, because the current, when you have an abrupt change of the current, the voltage across the diode changes, increases by a lot. And then if you do it, if you really have just a switch, the voltage can be extremely high. These are used, for instance, to make sparks, so spark plugs and so on. So in order to avoid the sparking, one has to offer an alternative way for the current. So when you open the switch, now this point wants to go up in potential, but this then opens up the path through the diode, so the current will flow. So the current will flow back to the input of the coil and can flow here for a while, and slowly being absorbed by any resistance in the circuit. So in this way, you prevent these voltage spikes across the inductor when you switch. So, and this inductor can be anything. It can be a motor, it can be a relay. So these should always have these so-called flyback diodes. So a good analogy here is that you can think of a diode. You can think of an inductance as a turbine with a massive wheel. So this turbine is in the flow of your water, and as long as the water flows steadily, then the turbine just rotates with a constant velocity. Then if all of a sudden the water stops flowing, your turbine will still turn and try to push the water out. So this water has to go somewhere. You'll see an extreme pressure on the other side. And in order to make this not be a problem, you can open this valve that lets the water go back to the input of your turbine. Okay, this is kind of the analogy of this flyback diode. Okay, so far we discussed the ideal diode. So we only thought of it as something that conducts whenever the voltage goes above a certain threshold voltage, or the diode voltage, which in most cases something like 0.7 volts for the silicon diode. From now on, we move on to real diodes. And the IV curve of a real diode is, of course, a little more complicated. And by real diode, I now mean a semiconductor diode, a semiconductor junction diode. So this is an example of an IV curve for such a diode. So here you have the voltage, here you have the current, where with the sign convention is shown here. So the positive voltage, the positive node is here. So when we are on this side, we see that the current rises steeply, and when we go to the other side, the current is very small. But for a real diode, it will eventually start to become large as well, and this is called a diode, a breakdown. And we'll also see that the current here in this region is not really zero, but there is a small reverse current, which is also a deviation, obviously, from the ideal diode behavior. So to understand the details of this curve, we have to look a little bit into semiconductor properties, and then look at the p-n junction. So we'll start with a small overview over semiconductors. We'll discuss some concepts here, the concept of an energy band. We need to look at electrons, holes, and charge carrier densities as you find them in semiconductors, the Fermi level, Fermi function. We also need to understand a bit about generation and recombination of charge carriers, then drift, diffusion, and mobility. So how do these things move around? And finally got to the important step for using this technologically, which is what is the effect of defects and doping. Okay, so let's say a few things about silicon. Silicon is, of course, the most dominantly used semiconductor material for electronic components. A silicon atom has 4 electrons in the outer shell, and atoms would like to have something like 8 in the outer shell, then it's most stable. Then before you start a next shell, you need a lot more energy. So 8 is usually a stable configuration. So when you put silicon atoms together, they arrange themselves in a way with 4 neighbors, and then they share one electron. And then each silicon atom is in this stable configuration where it has 8 electrons in its outer shell, where 4 of them are shared with its neighbors. So the 4 is from, of course, its position in the periodic table of elements. And then if you look around the periodic table, left and right, you will see all the other materials that play a role in semiconductors. So you can have germanium, which forms similar crystals, but you can also combine 3 and 5 elements. For instance, gallium arsenide is another important semiconductor. And the other elements that you see here, boron and phosphorus, for instance, are used as dopants for doping silicon. So these are all the elements that are important for semiconductor industry are very close together in the periodic table. Then when you have something in this configuration, and the picture now only shows, of course, a 2D picture. The real crystal is, of course, a 3-dimensional, but it's a little difficult to imagine. So with four neighbors, but in a 3-dimensional arrangement. So this is just a 2-dimensional picture. And all the electrons are bound. So and we have no movable charges. So these bound electrons cannot hop around. All the positions for electrons are filled, and we cannot move anything around. If you want to have conducting electrons, then we need to ionize these atoms. We need to basically rip an electron out of this grid away from one of the atoms. And this brings us to the concept of energy bands. So maybe you know that in single atoms, electrons have discrete levels of energies. They cannot have any arbitrary energy. They are restricted to certain discrete levels. When you have an infinite array of electrons, these discrete levels turn into bands. So we have certain regions, certain ranges of energies that can be taken up by electrons, and others are not available. And whenever you have a band that is completely full or completely empty, that means that all the electrons are in their place and they cannot move around. So in order to move around, an electron needs to change its energy, and it can only do that by going to an empty state. And when all states are filled, it cannot move, okay? Because no other energy state is available. So the minimum energy that you need to move an electron around is first you have to get it from a filled band into an empty state. And these empty states are separated by the so-called energy gap. So in an insulator, this energy gap is relatively large. So here you have a completely filled valence band. And if you want to get an electron to move around, you have to give energy to this electron to enter the conduction band. And this energy in an insulator is relatively high, much much too high to have an appreciable number of conducting electrons at room temperature, and that's why we call these things insulators. On the metal, on the other hand, there is basically no gap between the valence band and the conduction band. So in a metal, there are states directly above the valence band, so to speak, available. So there is no gap, and any electron can move around freely. That's why metals conduct very nicely. Semiconductors are somewhere in between. So the gap is relatively small. In case of silicon, it's 1 electron volt, 1.1 electron volt, and the conductivity is somewhere between the insulator and the metal. That's why they're called semiconductor. Okay, so the other concept that we need is that of electrons and holes. So when we ionize one of these atoms, so we give energy to an electron here and transport it into the conduction band so it can move around freely, we're left with an unoccupied state in the valence band. So there's one missing bond electron here, which is symbolized like a missing state, a not filled state in the valence band, and these states are called holes. So for every electron that we create here, we have a hole, and in a silicon crystal, both the hole and the atom can be considered or should be considered as real particles or quasi-real particles. So they can move around and they have a charge. So the electrons obviously have a negative charge, they can move around, but also the hole must be considered as a positive particle that can move around. So sometimes it's people say that, okay, this is now if an electron jumps from here to here, then this hole moved there. But the better way to really think about this is to look at this hole as a positive particle that can move around. Both are called quasi-particles because even the electron does not behave exactly like a free electron, but similar. And so you can you really need to think of holes and electrons in similar terms. So both of them move around in random motion. That leads to so-called diffusion. And if there's an electric field, then they also will follow the electric field and have a drift superimposed to this diffusion. This process of generating an electron, a free electron, by lifting it into the conduction band is called generation. Of course, we do not generate an electron really, but we lift it from the valence band into the conduction band, and we create a hole in the valence band. But from the point of view of conductance, which is important for us, we really create a pair of charge carriers. So we create a pair of a positive hole and a negative electron, because we don't really care too much about the valence electrons. They don't do anything for conductivity. Okay, so that's why this is called creation or pair creation, which is can either be thermal, so there's just a random excitation with phonons or whatever, and that makes this pair, or it can be done by radiation, which is used in photodetectors, for instance. Then the inverse process, where the electron then falls back down into the valence band and fills a hole, is called recombination. So here an electron-hole pair annihilates in some sense and just creates energy, which is usually then emitted as light. Silicon, for instance, emits infrared light, but in LEDs you have materials then that emit visible light. And the rate with which this happens clearly depends on the density of these carriers. So from now on, we will more and more not care about the valence electrons at all. And when we say electrons, we really mean the mobile charge carriers, right? And the holes are obviously the corresponding holes. It is important to understand that the situation, the occupation of these states is not static, but it's a permanent back and forth. So this is the result of a dynamic equilibrium of processes with different energy transfers. And you can only say that states are filled with a certain probability, and this probability is given by the Fermi-Dirac distribution, which is for fermions the equivalent that you maybe know already from the Boltzmann distribution for classical thermodynamics. I don't know, have people heard thermodynamics here? Okay, good. So this is the shape of the Fermi function. Here's the energy, and the probability to fill a state depends then on the temperature. This has two parameters. One is the temperature, or the width, which gives the width of the Fermi function when multiplied by the Boltzmann constant. So for room temperature, this parameter is about 25 or 26 millielectron volts. And the other parameter is the Fermi level, which is basically this position here, where it starts dropping to zero, or the 50% point of the distribution. So what does it look like when you have a semiconductor? So I've turned the band gap picture here by 90 degrees, and here you have the conventional to match the plot of the Fermi function here. So now the energy is on the horizontal axis, and the probability density is shown on the vertical axis. This is the Fermi function. You have the valence band down here, and the conduction band down here. The Fermi function, of course, describes all electrons, so valence and holes. But if you look, for instance, at the conduction band, the electrons are basically this part of the Fermi function that reaches into the valence band multiplied by the density of states. So this is basically what you see here, multiplied by some factor so that you see it. Then here, in principle, you would see all the valence electrons, but we are not interested in them. So what is shown usually is just the hole density, which is one minus the valence electron density, and this is seen here. And the Fermi level adjusts itself such that the number of holes and the number of electrons is the same. The density of holes and electrons is the same. Otherwise, it would not be neutral. So this is not a free parameter that you can just set, but it adjusts itself based on the available states. So if you had a lower Fermi level, like here, then you would have too many holes. And if you had a higher Fermi level, you would have too many electrons. So that's this parameter adjusts itself such that the total number of holes and electrons is the same, at least in a perfect silicon crystal. So normally we're not so much interested in the energy distribution of these parts of the electrons, but we want the spatial density, because this is what gives us the total conducting, the electrical properties. So if you integrate the Fermi function then multiplied with the density of states over the conduction band, you get the number of mobile electrons, and this is this expression that you get in the so-called Boltzmann approximation. So you have these constants, which are temperature dependent, so they're not really constants, but they characterize the material, silicon, for instance, and you have this exponential function of the distance between the band gap, the lower band limit, and the Fermi energy divided by the Boltzmann constant times temperature. And similarly for the holes, you get this expression here. So for a perfect crystal, you always have that the two are the same, which defines your Fermi level. And this density that you have then for holes and electrons is called the intrinsic density. And as I said, this condition fixes the Fermi level. So if you say that these two are equal, you can basically extract the Fermi energy from this, and it's usually very close to the middle of the band gap, plus a small correction that depends a bit on temperature. Almost more important is the fact that the product of the two, so when you take these two numbers here and multiply them, these two, this is what I'm doing here. So you multiply the hole density and the electron density, And then you get this expression, which is independent of the Fermi level. And this is, since they are the same, the square of the intrinsic carrier density. So the intrinsic carrier density is the square root of the product of these two constants multiplied by a function, exponential function of the band gap divided by the temperature. The fact that this product is constant remains unchanged by doping. So later we will change the number of free carriers by doping, but the product of the two remains the same, and that's because it reflects the dynamic process of generation and recombination. So if you increase the number of electrons, for instance, with doping, we'll see in a minute how that goes, then you have more electrons, they do more recombination, and this way they decrease the number of holes, and they do it in a way that the product of holes and electrons remains constant. This is also called the mass action law in chemistry, for instance. When you have two components that react with each other, then the product of the density remains constant. From the formula that we've seen before, you can put in the numbers for silicon, and you find that the intrinsic carrier density comes out like 10 to the 10 per cubic centimeter. This is the intrinsic density of carriers. There are two things to note. First of all, it has an exponential temperature dependence. So you have the energy, the gap divided by the temperature multiplied by the Boltzmann constant. So on top of the temperature dependence that you have here, you have an exponential temperature dependence. This you will see in many properties of semiconductors. You have extremely high temperature dependencies. So whenever you have semiconductor circuits, you need to worry about temperatures. And much of the effort in these circuits is about reducing the temperature dependence with proper circuit design. The other thing to note is that you can compare this number with the typical number of atoms per cubic centimeter in such a crystal, which is of the order of 10 to the 22. So it's many, many orders of magnitude smaller than what you have, for instance, in a metal. So intrinsic silicon, really pure silicon, is an extremely poor conductor because the number of electrons per cubic centimeter is so much smaller than it is in metal, for instance. The other thing to note is that intrinsic silicon basically doesn't exist because it's never so pure that you really can neglect that you really have this intrinsic charge carrier density. So there's this nice quote from Wolfgang Pauli that one shouldn't really work on semiconductors because it's such a mess and nobody knows whether semiconductors really exist. That is the frustration from the time when people try to understand and make experiments with semiconductors, and they never got good results because the behavior of these materials is really driven by contaminations. Okay, and that was for a long time. This was not under control. And but today, one basically turns this around and uses these contaminations to determine the properties of the silicon. So we still don't have a lot of intrinsic silicon, but one can have relatively pure silicon. But the real interest now is to introduce these impurities in a controlled way. So this brings us to defects. Crystals are never perfect, and when you have a defect, you introduce new states available for electrons in this crystal. So these states are often in the forbidden zone in the energy gap. So a defect can be an impurity atom, which is the doping that we'll talk about, but it can also be crystal defects when the arrangement of the crystals has a problem. Or it can be a boundary or surfaces. So surfaces of semiconductors are also always problematic. So these defects are typically localized, except when you go to very high temperatures. So that during production of semiconductors, these defects can be moved into the silicon by heating it very much, and then they diffuse. Yes. Okay. Thank you. I'll try the other one. Is this better? Okay, thank you. Okay, where was I? Yes, so during semiconductor processing, these defects can diffuse through the material at very high temperatures, but then at room temperature they fix. So they can be brought to the places where we want them, but then they don't move around anymore. So they produce these additional states in the energy gap, but they're localized. And now the important part is that the activation energy, so the energy that you need to move an electron from the valence band, for instance, into such a state here, if this is a state available for an electron, is much smaller than the energy gap. So that means that the number of ionized atoms is much higher. So the reason that the intrinsic number of carriers is so small at room temperature in silicon is that the gap is so large. So the gap, this 1.1 electron volt is much higher than the 25 millivolts of the Boltzmann constant times the temperature. But if you have a smaller distance between your valence band and your defect, then this is ionized much faster. And in this case, we created, for instance, an electron which is now stuck because it's attached to this localized defect, and we have a mobile hole. Okay, so we changed the number of mobile holes, but not the number of mobile electrons. Okay, and in this way we can have a difference between the number of electrons and holes. Yes, that's here. The thing is that the mass action law still holds, so the product of the two numbers will still be the same. That's why the intrinsic carrier density still shows up in many places where you don't expect it, because the material is not intrinsic. So there are two types of defects that are important in semiconductor technology, and those are the acceptors and donors. So what we've just seen was in principle an acceptor. So the ones that are used technologically are borons and gallium. So these are atoms with 3 shell electrons that we put into the silicon lattice in a position where a silicon atom would usually be. So this is indicated here. So you have this atom here, and then it has only 3 outer electrons, so one bond here is not satisfied, and that can be filled relatively easily. So if a valence electron wants to go there, it doesn't make a large step in energy. So this creates a new state that is just above the valence band here, 50 electron volts, for instance, which is then already close to the thermal energy. And then when you have, for instance, room temperature, this state is occupied, is surrounded by many other states that are these other bonds here that have almost the same energy. And if there's no real energy penalty in going there, then at finite temperature, it is just extremely unlikely that this position is unfilled and all the other ones are filled. Okay, that means at room temperature, if you have a small number of acceptors in this huge crystal with all these other states that have almost the same energy, then at room temperature, it's basically always ionized. Okay, that's the interesting part here. I'm going. So these holes will at room temperature be almost 100% filled, and then you're left for each of these atoms with a negatively charged defect and a hole that's floating around in the crystal. And because you now have more electrons, more holes, which are positive charges, we call this p-doped. Okay, so by adding a certain number of acceptors into our crystal, we get the corresponding number of mobile holes and mobile positive charges, and that's why we call this p-doping. And by doing this, we move the Fermi energy a little closer to the valence band. You can do the same thing if you use an atom that has 5 shell electrons and not 4. Now you have this situation. You have 4 bonds that are satisfied and filled, and you have another electron that is still bound but only very weakly. So it takes very little energy to get this electron away from this atom, and then it can float around freely. And this is indicated here. So this state is very close to the conduction band. It takes very little energy to get it out and move around. Similarly, again, we have this roughly 50 millielectrons below the conduction band, a new state. And when we ionize this, again, it's very unlikely that it's ionized, and then this electron can move around freely in the conduction band, and we're left with a positively fixed charge that is stationary. And because we increase the number of negative charges that are mobile, we call this n-doped. And in contrast to the case of the acceptors, the donor, in case of the donors, the Fermi level now moves a little bit towards the conduction band. Okay, see how much is there. Okay, maybe we continue next time then. Okay, thank you.